All right, class, today we're going to be, sorry, let me get my microphone in. All right, okay, hopefully that's better. We're going to be going over the ideal gas law in this lecture, finally getting to it. And we're talking about Avogadro's law as well. And we're going to start incorporating, maybe not too much in this lecture, but start incorporating that into stoichiometry and kind of tying the past like 7 lectures together. So hoping for this test, maybe some of you will find it a little more cohesive, I guess. The last one kind of seemed like we were just going through like random stuff, like radiation here, and then we're talking about periodic trends and kind of a bunch of random stuff. But I think hopefully this one you can kind of see how it all connects a little bit better. Okay. Let's start with this quiz. Go ahead and pause the video and try and do this one on your own. Okay, coming back. So question says that a 2-liter balloon is tied to a heavy rock and dropped into a deep mountain lake. So then we have the pressure of the mountain lake at 0.7 atmospheres and the temperature at 21 degrees Celsius. When the balloon reaches the bottom of the lake, the pressure is 9 atmospheres and the temperature is 3 degrees Celsius. What is the final volume of the balloon? So this part right here is kind of the initial, okay? This is initial. And then the last part here would be our final conditions, basically. Okay, so initially we have a 2-liter balloon, and it's put in a mountain lake. So let's see. Oh, okay, sorry. Yeah. So the atmospheric pressure in temperature right before it goes in the lake, I think this is what it's referring to, are these numbers. So still we'll consider that initial, right? So the initial pressure is going to be 0.70 atmospheres. And initial temperature is going to be 21 degrees Celsius, which should be 294 Kelvin. Okay. And you just, for Kelvin, you just add 273 to whatever the Celsius number is. All right. So then when the balloon reaches the bottom of the lake, so then we have, so this is our final volume, final pressure, and final temperature. Okay, we have a pressure of 9 atmospheres. And the temperature is 3 degrees Celsius, so that would be 276 Kelvin, right? What is the final volume? Okay, we're solving for volume. Okay, so you can see on this problem, hopefully you had some practice with this in the homework. We have volume, pressure, and temperature. So we're going to need a gas law that relates all 3 of these variables. Sorry, that should be a 1. 1 equals P2 times V2 over T2, right? Okay, and we have 5 of the 6 unknowns, so we'll solve for the 6th one, which is V2. So rearrange the equation to solve for V2, like that. And then it's a plug it into your calculator at that point, right? So you can see that the places to mess up on this are really, rearranging the equation. Sometimes you can mess up on that. And then also just putting it in the calculator is wrong. Sometimes that's almost the hardest part about these, is getting these all together. What I would recommend if you're having trouble is you can view this as a fraction if you want. 2.0 liters over 1, right? Anything over 1 is itself. Multiply all the numerators together, multiply all the denominators together, and then do it in your calculator. Or if you have a graphing calculator, it might be easier to do it all at once. But anyway, find out what works best for you in your calculator and solve for the answer there. All right, perfect. Moving on. So we kind of looked at this summary of the different gas laws that we've looked at so far. We're going to add a couple more in this lecture. What we haven't talked about at all is what if the number of moles change, right? So we have I guess we've talked about 4 laws so far, and in all those laws, the number of moles was constant. We haven't talked about what we would do if the number of moles change, okay? So if a balloon is leaking gas or being filled up with gas or something like that, or a chemical reaction produces or uses up gas. So to deal with number of moles, we use Avogadro's law. And this is Avogadro's law. And again, all these can be derived from this parent ideal gas law. I like to view it like that. So Avogadro's law deals with volume and moles. So that means pressure would be held constant, R is always a constant, and T is a constant. So if we rearrange this, we could divide both sides by N and both sides by P, and we would get V over N equals RT over P, right? We have V1, N1, this equals a constant. We've already done this a couple times. And the constant would also equal V2 over N2. Take out the middle, you have Avogadro's law, okay? And that's what we have here. So again, in this one, our temperature and our pressure are constant in this case. So let's see. Okay, so this is basically, there's no like valve here. This looks like the piston illustration, but you can see that the number of moles here, so each of these red dots represents like a molecule. If we double the amount of molecules in there, if the pressure is and the temperature the same, it's going to have to get bigger to accommodate more of the gas, right? So since these are proportionally related, if you double the amount of moles, you're going to have to double the volume, right? So we went from 1 liter to 2 liters of volume. Okay, so this is Avogadro's law. Okay, sorry, forgot to pull out that slide. This is a demo, and sorry, we're not going to be able to do this one. Okay, don't worry about the slide. Sorry. Okay, all right. So talking about volume in moles, the ratios of gas volumes are identical to the ratios of moles. Okay, so basically just kind of reiterating the fact that volume and moles are proportionally related. You can take this, right, if this equation here, if you divided both sides by V2 and then multiplied both sides by N1, you could actually rearrange this equation here to get to this one. And so that is telling you that the ratio between the volume is equal to the ratio between the moles, right? We haven't done this with the other ones because it's really only useful with Avogadro's law, because by doing this, it tells us that we can interpret stoichiometric coefficients as volume ratios, okay? Again, as long as there's a constant temperature and pressure. So for example, we can say that 1 liter of nitrogen gas produces 2 liters of ammonia. Before, we used to only be able to say that 1 mole of nitrogen produces 2 moles of ammonia, right? We've done that before with our mass calculations. We use the mole ratios to say 1 mole of nitrogen produces 2 moles of NH3, and the 1 and the 2 come from the coefficients in the chemical equation. This isn't true with mass, right? We've never been able to say that, you can't say that 1 gram of nitrogen produces 2 grams of ammonia, right? You can't use the coefficients for mass, right? This isn't true, okay? Make sure you don't like write that down as a note and then think it was something I said was true. You can only relate mole ratios up to this point. Now, using Avogadro's law, because the mole ratio is equal to the volume ratio, you could also say that 1 liter of nitrogen produces 2 liters of ammonia. And again, you need to make sure that if you're going to use this may be useful as you solve some kind of problem, homework or something. If you're going to use this, temperature and pressure must be constant, right? Because this is only true when Avogadro's law is applicable. And Avogadro's law is only applicable when temperature and pressure are constant, right? And it's also only true when these are gases, right? You couldn't say, if it's, if it was like water and something else, right? In the liquid phase, it wouldn't apply, only in the gas phase. Okay, so it can be useful, but it can also be, I don't know, can be used incorrectly sometimes, easily. So just make sure if you're gonna use that to solve a problem, those things are true. And hopefully you'll come across some examples of that more. This is kind of an example to show you the point, but let's go ahead and try and do it with this problem. Okay, so you'll see as we move along that there's multiple ways you can actually solve this problem right here. Using what we just talked about is the easiest way and the quickest way. As we explore the other ways to solve a problem like this, I'll point that out, and you can kind of figure out what works best for you. But anyway, go ahead and pause the video and try and solve this one so far. All right, so the question says, if you start with 125 liters of hydrogen gas, how much ammonia gas will you produce? So we're going to assume temperature and pressure are constant, okay? And these are all gases. So that means we can use Avogadro's law, right? Avogadro. Right, that's going to work for us. Avogadro's law tells us that V1 over N1 equals V2 over N2. If you rearranged it, you could say that V1 over V2 equals N1 over N2. So the molar ratio is going to be equal to the volume ratio. So if we start with 125 liters of hydrogen, okay, we can convert to liters of ammonia just using the mole to mole ratio or the volume ratio, because they're equal, because we can use Avogadro's law. So that tells us that 3 liters of hydrogen gas produces 2 liters of ammonia. That's just using the coefficients from the equation. And you go ahead and solve that, and you can get your answer pretty quick. Sorry, I drew over the answer. Okay, quickest and easiest way to do that is using Avogadro's law. Although you just have to remember that if you're going to use this little shortcut, temperature and pressure are constant, and they have to all be gases. Okay. What if we need to convert from volume to moles? We haven't talked about this conversion yet. So usually we've talked about converting grams to moles, right? I always say you're going from grams of A, right, to moles of A, and then you go on, right? And this conversion uses molar mass. We've talked about that. But to convert volume to moles, we're going to need a molar volume. That's the term that we're going to use, okay? So the nice thing about this is that every compound or element has a unique molar mass, right? So if it's carbon dioxide, the molar mass is 44. If it's water, the molar mass is 18. They're all different. For a gas, at standard temperature and pressure, as long as it's at standard temperature and pressure, then the molar volume is the same for all gases. Doesn't matter what gas it is. All you have to remember is that 22.4 liters contains 1 mole of particles. Okay, so standard temperature is 0 degrees Celsius at 1 atmosphere. Okay, so as long as the problem, and the problem usually says at STP conditions, or it may give you, it may say it's at 0 degrees Celsius and 1 atmosphere of pressure, in which case you would know that it is standard temperature and pressure. And again, all gases have the same molar volume at standard temperature and pressure, which is really nice because then you don't have to have another number to look up or whatever. You can just know that 22.4 liters contains 1 mole, so you can make conversions like this. Okay, using that, using this formula. Cool. So we have another way to get to moles, right? So if we start with volume of A, we could go to moles of A using the molar volume. Okay. So this is just kind of a little illustration to show the point. So 1 mole of helium, if you convert from moles to grams using the molar mass of helium, you'd find that 1 mole of helium weighs about 4 grams. Okay. Let's see. Yeah, 1 mole of helium weighs 4 grams. Okay. And occupies 22.4 liters. Well, 1 mole of oxygen, it actually weighs 32 grams, so the balloon itself would be a lot heavier, but the volume is the same. So you can see how the molar mass between helium, oxygen, and nitrogen are different, and that's why from moles to grams you have such different numbers. But the molar volume is the same regardless of the gas because we're at standard temperature and pressure for all these, right? Standard temperature and pressure. So 1 mole is 22.4 liters for all 3 gases. Okay, just showing that their molar volume is the same as long as it's at standard temperature and pressure. Okay. All right. So let's try this problem. You can go ahead and pause it if you want and work through it. Okay. So this is pretty much the same problem we just looked at, right? In this problem, in the last one though, you'll notice ammonia can be in 2 different phases. In this scenario, ammonia is actually given as a liquid. So we can't use Avogadro's law because Avogadro's law only applies if it's a gas, right? We talked about that. So we're not gonna be able to use that little shortcut that we did before. So in this question, it's saying we start with 120 liters of hydrogen gas. How many grams of liquid ammonia will you produce? Okay, so I'm going to start by just drawing out maybe a portion of the little map that I like to use. Okay, so usually what we've seen so far basically is grams of A to moles of A over to moles of B and grams of B, right? That's all we've really had to deal with so far. Okay, well, if I add another piece to it, I could say I could go from the volume of A directly to moles of A. If it's at STP, then all I need for this is a molar volume, right, that we talked about. Okay, and then you could go from moles of B, you could go to volume of B. If it's at STP, and if it's a gas, right, again, using the molar volume, okay? And this would have to be a gas. Okay. I'll try and put out a more complete map of this that you guys can all use as you're studying and stuff. Again, and then grams to moles, again, this is the molar mass, right, for both of these. Okay, so the problem says we're starting with hydrogen gas, so hydrogen gas is going to be my A. We're seeing how many grams of liquid ammonia we can produce. So I'm going to label ammonia as B. So I start with a volume, right? This is where I'm starting. Make that large. And I need to go to grams of ammonia. So I need to go to grams of B. So I'm actually going down here. Okay. So my path, obviously, is going to be go to moles of A, and then over to moles of B, and then down to grams of B. Okay. So start with 125 liters of hydrogen gas. Hydrogen. And then I can go from liters of hydrogen to moles of hydrogen because we're at STP and the hydrogen is a gas. So we'd say 22.4 liters of hydrogen is 1 mole of hydrogen gas. Okay. Then we can go from moles of hydrogen to moles of ammonia, right? We're crossing the mole bridge here. So every 3 moles of hydrogen produces 2 moles of ammonia, right? So now we just went from moles of A to moles of B. Now we need to go from moles of B down to grams of B. And so this time we're going to be using the molar mass. So 1 mole of ammonia weighs about 17 grams. Okay. And then we have grams of B. Cool. Let me pull out of this and just have the slide walk you through it now. So the exact same things we wrote out, right? And you get to your answer. Okay, so hopefully you can see how that map hopefully can help you get moving across from one to the other. And like I said, we've been using that for the past quite a few lectures. So it's a really big idea, obviously, on exam 2 that's coming up. Is going to take a lot from that, probably. Okay. All right, so we've talked about how to deal with gases in chemical reactions in 2 different ways so far. You can either interpret the stoichiometric coefficients as volume ratios, right? This is only in cases where Avogadro's law applies. So you have to have a constant temperature and pressure, and they both need to be gases, whatever you're converting between. And then we also talked about converting volume to moles if you're at STP conditions. And that's the one we just did, where at STP, we can say that 1 mole equals 22.4 liters of gas. And then you use the mole ratios like we've done before. Use mole ratios like normal. So the 2 problems we did are the 2 different approaches that we talked about so far. The only other thing we need to talk about is what if we need to convert from volume to moles, but we're not at STP and we're not in a case where Avogadro's law applies. Okay, so basically we need another rule that's just going to cover every other scenario. Approaches 1 and 2. It's kind of like you can, these are really shortcut methods and almost the go-to if you can. This last one we're going to talk about that covers really the rest of them takes a little longer, I guess. You need more numbers and a few more calculations, but it covers a much larger variety of problems, basically. But I would say it's important to just know all 3, okay, and how to deal with gases in a chemical reaction. All right. So yeah, you could use the combined law and determine what the volume would be at STP, and then convert that to moles. It's kind of annoying. So we're going to talk about it the easier way, and that's the ideal gas law that I've been talking about in the last few lectures, the last 2 lectures. And I keep saying we're going to learn it, we're going to talk about it, and we're saving it for last. The ideal gas law helps us determine or convert from volume to moles if we're not at STP. It can also help with a lot of other things too. But we've learned already so far that pressure and volume are proportional to moles and temperature. And they're not like perfectly 1-to-1 in all cases. There's a constant basically that needs to scale the right side. Don't worry about that too much, but R is a proportionality constant to give you the right proportions. So PV equals nRT is the ideal gas law. So N obviously equals the number of moles. So we can convert from volume to moles, so from volume to moles at any pressure and at any temperature using this ideal gas law. That's basically what we got here. You can also convert from moles to volume, right, at any temperature and pressure. You just fill in your temperature and your pressure. It's a customized You can figure out your volume. Okay. Figure out temperature, right? Anything. Okay. R is the universal gas constant. Here's kind of a derivation of it. Okay, so if you rearrange the ideal gas law, you can say that R equals PV over NT. Okay, R equals PV over NT. That would be the rearranged ideal gas law. Okay, well, at standard temperature and pressure, we're at 1 atmosphere with 1 mole. Oh, sorry. Yeah, we're at 1 atmosphere and we're at 273 Kelvin temperature. Also at standard temperature and pressure, 22.4 liters is occupied by 1 mole of gas. And so because we know all these are true, plug in those numbers, we can solve for R. Don't worry about solving for R. I'm not going to ask you how to solve for it or anything. So anyway, that's a random factoid. Don't worry about it too much. But if you're curious, that's how you can solve for R. All right, and then R, because it's a constant, is going to be true at any pressure and temperature. So now that we have R, we can use it in other situations. Okay, go ahead and try this practice problem real quick. All righty. Okay. Question says, how many moles are in 5 liters of oxygen gas? The pressure is 0.75 atmospheres and the temperature is 50 degrees Celsius. All right, so we're solving for moles. So I'm just going to list all of our variables here. We have P, we have V, we have N, we have R, and we have T. Okay. We're solving for moles, which means we're solving for N. R never changes, it's a constant, so it's 0.0821. And the units are liters, atmospheres over moles times Kelvin. The reason the unit is important is it tells you that you need your pressure to be in units of atmospheres, you need your volume to be in units of liters, you need N to be in moles, which it always is, and you need temperature to be in units of Kelvin. If the problem is giving you a volume in milliliters, you can't put it into this equation unless you convert it to liters first. Same thing with pressure. If the problem gave you a pressure in terms of torr or millimeters of mercury, you need to convert that pressure into atmospheres before you can use it, because R only works when it has these units alongside it, basically. Okay. All right. Let's see. Moles are in 5 liters of oxygen gas, so that's going to be our volume is 5 liters. And pressure is 0.75 atmospheres. Okay. And the temperature is 50 degrees Celsius, which would be 323 Kelvin, I believe. Okay. Well, we have 4 of the 5 variables, so we can just plug it in and solve for N, right? We want to rearrange it to solve for N. And then you plug in your volume, your pressure, your R, and your T, your temperature. Lots of numbers. All your units cancel out except for moles. And since moles is in the denominator of the denominator, it comes up to here. Anyway, if you are a unit person, you might find that fun and interesting. Okay, and you get to your answer. So I'm hoping you can see with all these gas equations, biggest thing I think is keep using the right units and putting in your calculator correctly. It's going to be a big part of getting these questions correct. Okay, so be very careful as you do it. You can always check your answer too, right? So for example, if you were on a test and you're worried that you might get it wrong, let's say you put it in your calculator and you got 0.14 moles. Well, you can now put that in for N, right? You can multiply N times R times T, and then you can multiply P times V separate and just make sure they equal each other. And then you know you got it right, right? So you can check your answer really before submitting it by doing it that way. Okay. All right. Go ahead and try this example as well on your own. See how it goes. All right. So question says you have a 3-liter balloon at 0 degrees and 0.7 atmospheres. You let it go and it floats away, eventually reaching an altitude where the temperature is -25 Celsius and the pressure is 0.5 atmospheres. To make things more complicated, half of the gas has leaked out of the balloon. Okay, so if this last sentence wasn't added, right? We could, you could, this part right here, you could find the final volume with just the combined gas law, right? The stuff we did in the last lecture. But the problem with the combined gas law is it assumes that the volume of, or sorry, not the volume, but the number of moles of gas remains constant, right? So this is the kicker. To make things more complicated, half of the gas has leaked out of the balloon. Okay. All right, so let's just start and let's look at what we have. I intentionally don't solve these problems beforehand because I kind of want you to see me work through it. If I had already worked this out in my head, I feel like I might miss something. So this is a more complicated problem, but let's work through it. Okay, so let's just say initially we have a volume of 3.0 liters. I always just like to write it down in a lot more simple terms because it's just complicated if you're sitting there staring at the problem. So if you're in the test and you don't know what to do, start writing stuff down. Don't just sit there. Okay. And we have an initial pressure. Okay, so sorry, yeah. Initial volume is 3 liters. Initial temperature is 0 Celsius, which is 273 Kelvin. And our initial pressure is 0.70 atmospheres, right? Okay. And then we have, sorry, kind of all over the place. Our final volume is what we're trying to calculate. Let's see. Okay, it reaches an altitude where the temperature is -25 degrees Celsius. So let me just pop that into the calculator real quick. 273 minus 25 is 248 Kelvin. And our final pressure is going to be 0.50 atmospheres. So you can see at this point, right, we've seen this before, like, oh, I could just use the combined gas law, right? Super easy. Well, the problem is the number of moles is not constant. Okay, so that's going to make an issue. You also can't use Avogadro's law because Avogadro's law says that the temperature and the pressure are constant, right? Okay, so the way I would solve this problem, and there's probably a couple ways I guess you could do it. We need more numbers, right? The ideal gas law is PV equals nRT. In order to use this, right, I would need to know actually, sorry. Yeah, we can use this. Okay, sorry, I just realized. We do know R. R is the same all the time, right? 0.0821, okay? Units are liters, atmospheres, over moles, times Kelvin. Okay, that's a lot to write out every time, so I'll probably just write it once. Okay, so I know pressure, I know volume, I know the gas constant R, and I know the temperature. So what I don't know is how many moles we have initially, right? Okay. I also don't know how many moles we have at the end. But I do know that half of the gas leaks out of the balloon, okay? So I'm just gonna leave this kind of blank for now. I don't know the moles at the end, okay? All right. If I knew N here, so PV equals nRT. Okay, I'm trying to find the final volume. If I knew N, then I also know pressure and temperature. So if I knew N and I know, shoot, I don't know volume. That's a question mark. But I know pressure and temperature, and I know R because it's constant. Because I know P, N, R, and T, I could solve for V, right? So what I really need to do is figure out N. That would allow me to solve for the final volume, which is what the question's asking, okay? The only thing I know about N is that half of the gas has leaked out of the balloon. If I can figure out the initial amount of gas, the initial moles of gas, all I have to do is divide that by 2 and I can figure out the final amount of gas in the balloon, right? Because half of it leaks out. Luckily, I can use the ideal gas law to figure out the initial amount of moles in the balloon. Okay, see, I'm getting excited because I like these kind of problems. I know some of you might get a little frustrated that sometimes problems aren't the exact same that you see in the homework or the lecture, but my goal is that you get the principles, okay? And that's what chemistry is all about. Teach the principles and let you figure out problems, because that's what's really useful in life, right? Anybody can learn something and just, you know, have it written down and regurgitate it or something like that. A really awesome skill, though, to have is to be able to figure things out. And that's what chemistry is all about. Okay. All right, so let's figure out the number of moles initially in this problem. So we're going to take, we need to solve for N, right? So we're going to rearrange this. So N equals PV over RT, okay? So our initial number of moles is going to be our initial pressure, which is 0.70 atmospheres, multiplied by our initial volume, which is 3.0 liters. That's a parentheses. That's an L. My pen is lagging. Divided by R, which is 0.0821 liters atmospheres over moles Kelvin. Okay. Okay. R times T, which is 273 Kelvin. Okay. Oh my goodness. Okay. So let's work this out. I am just using my phone calculator here. So I'm going to multiply the numerators first. So I'm going to do 0.7 times 3. That gives me 2.1. Sorry, that's very messy. 2.1 over, and I'm going to multiply the denominators, 0.0821 times 273, so divided by 22.4, and then I can just do 2.1 divided by 22.4. So I get 0.0937 liters. Okay, we're in liter, no, sorry, not liters. This is moles. Okay, so this equals N1. Okay, so again, I say this a lot, but if you're stuck on the test, just start doing, like, write down what you have and be like, oh, I could calculate this with that, and so just calculate it. It may or may not be useful, right? But we knew we had a volume, a temperature, and a pressure, and we always know R. So we knew that even if we didn't know where we were going, we could say, all right, well, we could calculate the number of moles initially using these numbers in the ideal gas law. And then once you get the number of initial moles, the light bulb might have gone on and said, oh, it says that half of the gas has leaked out of the balloon. Well, what this really is saying in terms of an equation is that N1 equals 2N2, right? So if half the gas is leaked out, you could also say N1 over N2 is going to equal 2, right? Because half of it goes away. Okay, however you want to look at it, that's fine. Or you could say half of the gas leaked out, right? So we know initially we have 0.09375 moles. Well, if we divide that by 2, it tells us that our final amount of moles is going to equal 0.046875. I think all the writing on this is making it go really slow. Okay, so that tells us N2. All right, so now we got N2. So now let's look at the second half of this problem. We know N, so we can take the the pressure volume equals N RT, right? Okay. So we know the initial pressure. We have that one. We don't know volume. That's what the question's asking. What's the final volume? We now know the final number of moles. We just figured that out. We always know R, and the problem gave us the final temperature. So now we can solve for the final volume, okay? So if we rearrange this, volume is going to equal nRT over P. Looks like pi. nRT over P. All right. So N is going to be the 0.04. I'm just going to round it to 0.047 because we're limited by like 2 sig figs on most of these, and that's 2 sig figs. So I'm just going to leave it at that. You could leave the whole thing there if you want and round at the end. It's up to you. Okay, so that's N. R is 0.0821 liters atmospheres over mole Kelvin. And then T is going to be 248 Kelvin. I promise my handwriting is not this bad in real life. This makes me look so sloppy. All right, and then we're dividing it by the initial pressure, that's P, which is 0.50 atmospheres. Okay, so if I put this in my calculator, I'm first just going to multiply all the numerators together. So 0.047 times 0.0821 times 248. I'm going to divide all of that by 0.5, and it gives me 1.90885. Okay, and that is in liters. Yes, liters. Okay, so now what I would say is kind of check and make sure that makes sense. So 3 liter balloon down at 0.7 atmospheres. If the pressure outside the balloon decreases, so like in this example, it goes to 0.5 atmospheres, then I would imagine that balloon would expand, right? The problem is that the temperature also decreases, which makes the balloon contract, right? So I guess it's kind of hard to envision in your head. You could check it just by plugging in your numbers and working backwards, I guess. But, well, yeah, I don't think that would really work too much. So, sorry. I guess on it says half of the gas has leaked out of the balloon, right? So, although this isn't perfect, you lose a lot of the air, the balloon would probably shrink in size, right? Okay. All right. Now I think we're limited by 2 sig figs here on all these. This one is reported in really 0 sig figs, but it's reported to the well, I guess the 1 decimal place. And then when you add the 273, you would have 3 sig figs. Anyway, we're going to be stuck with 2 sig figs for our answer here. So this would round to 1.9 liters. Okay. And if you got like 2.0, 2.1, 1.7, those are all essentially the same with regards to significant figures. So let me just lost all my work. That's okay, I was trying to do that. Okay, here's how the slide represents it. This is another gas law that you can memorize if you want. Okay. Basically, what I did before, if it made more sense to you, just stick with that and go with that. If it didn't make sense and you'd rather just memorize this, you can go with this too. But basically what I said before is, P1, we were relating everything through R, right? And so I'm going to derive this again. My pen is fast again now that I lost all that stuff. Okay, so in this question, the only thing that's constant is R, right? So we can say that PV over NT equals R, okay? So we could say, just like we've done in all the past ones, this is some constant. And since it's a constant, P2 over V2, sorry, P2 times V2 over N2 times T2 is also going to equal R. And then you can get rid of the R and put them together, okay? Another way to do this problem. Essentially, it's the same thing, but anyway, different way to look at it. I don't want you to try and learn both. If one is confusing to you, just drop one and learn the other way. Okay. If you prefer this way and you're like, wow, he's not very smart, he should have just done it this way, then yeah, I don't know what to say about that. But I like to think through the problem more logically, I guess, than just memorize equations. That's what I'm going to say about that. All right. So we can write out what we know and what we don't know, okay? Ooh, and then you rearrange the problem to give you this right here. All right, you're solving for V2. Okay, so if we look at just the initial numbers here, okay, we know that V1 equals 3 liters, P1 equals 0.7 atmospheres, and T1 is 273 Kelvin. We don't know what N1 is, right? We don't know what V2 is, we're solving for it. P2 is 0.5 atmospheres, T2 is 248 Kelvin, N2 is 1/2 N1, right? We don't really know what N1 is, but we do know this relationship. So what you could do here is actually, instead of N2, you could substitute it for 0.5 N1, right? Because we know that N2 equals 0.5 or 1/2 N1. So you could substitute it in. The N1s just cancel out, or you could, essentially what you're doing here is arbitrarily assigning N1 a value of 1 or something. But it doesn't matter. The N1s cancel out, so you can actually then solve for 1.9 liters. Oh, look, we hit it exactly with a different method. Anyway, So pretty cool. If you're feeling overwhelmed by this question, this is a challenging one. Don't worry. This would be, you know, like a question you see at the end of the exam, right? The big challenge question, stuff like that. So, but hopefully it's making sense to you, and I know you're going to feel good once you keep practicing it when you're able to answer these questions, okay? All right, so that was a little bit lengthy there at the end. Sorry that it got pretty intense with math and stuff like that. But hopefully it's making sense, and we're going to be talking more about stoichiometry with volume, and I think that will be, for some of you, you're going to like that a lot more than these like story problems about balloons and stuff like that. But just keep practicing in the homework, and remember, just look for principles and understanding the principles as you work through the problems. I think that's very useful. So, all right, we will see you next time.